Okay, we have Sasha Shapiro from Edinburgh, and he's going to apparently talk about our joint work on Ruijsenaars wave functions as SL2Z matrix coefficients.
Hi, thanks so much. Right, so I think I had a slightly different title. I promised something about Ruijsenaars and Toda integrable systems, but yeah, well, at least both words are on the board. Right, so this is joint work with Philip, Rinat, Sergei Horoshkin, and Gus Schrader, and this story is and very connected to the previous talk in many ways. I'll try to highlight it maybe. So both Ruijsenaars and Toda, in principle, they're continuous integrable systems. But again, I'll highlight some discrete flows that will appear here. So if you don't like continuous but like discrete, just bear with me, they will appear here. And what I'd like to discuss some strategy to obtain eigenfunctions of Hamiltonians of Ruijsenaars system. Not that it's new, obviously the Hamiltonians and their eigenfunctions, they're known, there are different expressions for them, but I'd like to discuss certain strategy, which at least we believe is maybe somewhat new to getting those. I write Ruijsenaars wave functions because the representations that will appear, or rather space on which these Hamiltonians will act, it will be space of L2 functions. But if you don't like L2 functions and you like polynomials better, you can still act on polynomials, and then eigenfunctions of these Hamiltonians will be just Macdonald polynomials, right? So if you like Macdonald polynomials, it's also in here. The way that I'd like to obtain these wave functions will be via understanding SL2Z action on the space that our Hamiltonians will act on. And to get this SL2Z action, we'll need quantum cluster varieties, which I believe the classical version was explained by Misha last week. Yeah, so this will be the main tool, this SL2Z action. And another tool that will appear here will be the quantum open Toda chain. And the strategy and most of the story that I'm going to tell works for SLN, but today I'll just focus on SL2 example. And again, I'll highlight which we know for SL2 and which we know for SLN. Right, so before I go to integrable systems, I'd like to discuss the Hamiltonians of the system via understanding them as some commutative subalgebra in a slightly bigger algebra. So this is a story due to Cherednik. And this bigger algebra is spherical double affine Hecke algebra as Daha. Again, I'm just considering this for SLN. And this algebra kind of lives on a punctured torus. So what does it mean that it lives on a punctured torus? That means that you take the first homology, or well, I've written cohomology, whatever, of the punctured torus, which is just Z2, it's a two-dimensional lattice. And for any element in Z2, I'm gonna have an operator, which is an element of this algebra. On top of that, we'll have an SL2Z action on this algebra, and it's kind of clear why it should appear, right? Because SL2Z is just the mapping class group of the torus. And the way it will act on spherical Daha, so the set of elements that I said we will have, right, they're just labeled by some vectors in Z2. And so if you take element of SL2Z, act on EV, you will get EG applied to V, right? Where V is a vector two-dimensional vector, and G is SL2Z matrix. And another useful theorem is that we actually know the generators of the spherical Daha. So if it's SLN version, then it's generated by EK0 and E0K for K running from 1 to N. All right. Now, what's the mapping class group? So, well, the definition is you take any surface and any oriented surface, and you take orientation preserving homeomorphisms modulo isotopy, and that's a very nice definition. But of course, it's impossible to work with this one. But luckily, you have some Dane twists which generate the group, and Dane twist just works as follows. So as you see on this picture, this green Dane twist is You take this green cycle, you cut along the cycle, you twist 360 degrees, and you glue back. And that's the result. That's what you see happening with the orange cycle when you do that, right? So that's Dane twist. And this mapping class group is just generated by all the Dane twists. And again, sort of getting ahead of myself, these elements of the mapping class group will actually give us some discrete dynamics. All right, so more concretely, there is a faithful representation of spherical Daha. And what I'm going to do now, I'm going to explain how to embed the spherical Daha into an algebra of Q-difference operators. So if you didn't like previous description, you can just forget it, and I'll just tell you explicit Q-difference operators by which this algebra is generated. So remember I had the elements EK0 and the E0K. So EK0 will become a multiplication operator. Yes, please. Sorry.
Just maybe I missed a point in the previous slide. So what is special about the EK0, E0K? Are they distinguished elements in your?
I can choose those as generators of the algebra.
Okay, they generate.
But they're just the generators. Yes, it's written over here. But I could have chosen other generators as well. It's just like, well, it's one choice. So I basically choose two basis vectors in Z2 and take all vectors in these two directions.
Okay, a priori they are not determined by symmetries, but they can be independent. But
come again?
They are not determined by the previous data.
Sorry.
A priori they are independent. The EK0.
Oh no. These guys are independent, but EVs are of course not independent. So yeah. There are some relations on EVs for different V's, but these guys are independent.
Okay.
Yeah. And it's the fact that they generate it's SLN. So for GLN, for example, you will need something extra. In fact, I think for SLN even E10 and D01 generate actually. That's true, right?
Possibly you need to include the k equal -1.
Right. Yeah. Good. So right for SLN. Which is true. What is true is that E10 and D01 generate the whole thing, but for GLN you will have to include as well E0 -1 and D -10. But it's just whether your determinant is 1 or not. Yeah. Right. So in the faithful representation, EK0 just becomes elementary arithmetic function, just multiplication by it, and E0K becomes Macdonald operator. Now here lambda and t is just a shift in lambda, so ti lambda j is q to the delta, Kronecker delta lambda j ti. An example for n equal 2, so well for n equal 2 we just have one symmetric function which is lambda plus, we have one lambda 1t, so the only symmetric function is lambda plus lambda inverse, right? And Macdonald operator becomes this guy over here. So the field over which we're working are rational functions of two variables, q and t. Q is our quantization parameter. T is some extra variable which just lies in the center, commutes with everything. So this lowercase t is that variable, and this uppercase t is the shift. So this is Q-difference operator.
So in the case of n equal 2, you have lambda 1 and lambda 2, and in the case of n is 2, you have lambda 1 and lambda 2.
Well, if it was GL2, I would have, but it's SL2. So if it's the difference between SL2 and GL2 is that I just ask lambda 1, lambda 2, their product to be equal to 1.
Okay.
And that's why, so in principle, here I should have had lambda 1 plus lambda 2.
Yes.
And I should have had another elementary arithmetic function, which is their product, lambda 1, lambda 2.
Yes.
But if it's SL version, then I just ask the product to be 1, and it becomes lambda plus lambda inverse.
I see, thanks. And I have one more question. So you assume that Ti and lambda j, say, it is a, how to say, QR pair.
Yeah.
I mean, then T and lambda are commuting.
Yeah, T's commute, lambdas commute. This is the only non-trivial relation. Yes.
Okay, so in the last line in your slide, the order of T and lambda is important. You mean T and lambda are not commuting?
T and lambda do not commute, yes.
Yep.
T lambda equals Q lambda T.
Yeah.
Yes. But, yeah.
Thank you.
Okay, cool. All right. So indeed, in this setup, what should be the strategy for obtaining eigenfunctions of these operators? Well, what I want to say is that if we had an SL2Z equivariant representation of our algebra, it would be done, right? How so? Well, remember we have multiplication operators and some complicated q-difference operators. And if you try to act by multiplication operators on a set of polynomials, obviously you don't have any eigenvectors. But if you act on more general functions or better distributions, then delta functions are eigenfunctions for multiplication operators, right? So you have a multiplication operator, you take a delta function, you multiply delta function by ek of lambda, and it's the same as multiplying by ek of x if your delta function was delta of lambda minus x. So this is here an eigenvalue, and this is an operator, right? And therefore, if indeed you have SL2Z equivariant representation, right, then, and you want to find functions of E0k, what you have to do, you have to take an element of SL2Z that takes vector 1, 0 and sends it to vector 0, 1. And then E0k is this matrix S applied to EK0, right? Because it sends K0 to 0k. And so if you knew eigenfunction of this guy, which was multiplication operator, so you knew its eigenfunction, it was delta, then you know eigenfunction of that guy, right? You just need to take this product of delta functions, or single delta function if you're in SL2 case, and apply element S from SL2Z, right? And that's the only thing you need to do. And this is Ruijsenaars wave function, just that. Well, unfortunately, if you're looking for actual McDonald polynomials, you can't do that, right? Because first of all, as we discussed, multiplication operators don't have eigenvectors in polynomials. And second, polynomial discharging representations that we've seen on the previous slide, it's very well known that it's not SL2Z equivariant. So we need to rectify that. We need to allow more general functions, and that's what we're going to do. Okay, that's the strategy. So in order to do that, we'll need to employ cluster varieties, and I'd like to make some digression and explain sort of the geometry of this story that I'm talking about now. And geometry involves this world of character varieties. And here's what it is. So we start with a surface, oriented surface with punctures, and the group G. And then what we want to consider decorated local systems. So what's a decorated local system? What's a local system, first of all? A local system is just a homomorphism from fundamental group of the surface to G. So in other words, you take pi1 of the surface, you take generators of pi1, and to each generator you say, well, this generator goes to this element of G, this generator to that element of G. As soon as you've said that, you're fine. Well, I mean, obviously relations have to be preserved. So that's the local system here. Now, decorated means that there's just a bit of extra data, and this tiny bit of extra data is just a choice of a flag at each puncture, which is invariant under monodromy around that puncture. And again, this is something very, very easy. So imagine that you have a monodromy that's some generic monodromy, right? Then how to choose a flag that it preserves? It's the same thing as just ordering eigenvalues of this eigenvalues or eigenvectors of this monodromy. Well, first flag subspace is an eigenvector. Second is spanned by the first two eigenvectors, and then third by the first three eigenvectors, and so on, right? So this is some discrete additional data, which is just ordering eigenvectors of these monodromies, just that. Now, that thing here is space of decorated local systems. And PGS is a moduli space of decorated local systems. So if I have these local systems, I still have an action of G, which just acts by conjugation on all this data, all action flags on the left, and by conjugation on all these images of this homomorphism. So in principle, I have to be slightly careful here, because if I just take space of decorated local systems, then G does not act freely, it has stabilizers. if I try to take a quotient, I get a stack, and it's a bit annoying. But what people usually do, they take some open subspace on which G acts freely without stabilizers, and then you can actually take this quotient, and that becomes a variety. And to take this open subspace, you just ask that all the monodromies, all the flags, everything is in generic position, and then G starts to act freely, well, provided your surface is not entirely trivial. And you get a variety, and this variety is famously a Poisson variety. So it has a Poisson bracket that's known under many different names: Atiyah-Bott, Goldman, Fogg-Crossley, Fogg-Goncharov, all possible, there are many people who work on this. This variety has Poisson structure, therefore we can quantize that, quantize functions on that variety. Yes, of course.
Probably not.
You don't, if you allow punctures, just punctures you don't. Punctures is like having a regular pole, order 1 pole. To have Stokes data, you need to have higher order poles, and you very much do have that in the story, but for that you need to allow boundary components with marked points. That's part of the story, just not the story that I'm going to tell today.
Okay, thanks.
Right. So, as I said, this variety has Poisson structure, and we can quantize that, right? So this OQ of PGS just quantized algebra functions. Mapping class group obviously acted on the surface, so it acted on your moduli space of local systems, and therefore it acts on your quantized algebra functions. Now, in the case of a punctured torus, gamma S is precisely our SL2Z, right? So that's why we have SL2Z action. Now we're gonna do slightly refined story. So remember how I asked that all the monodromies have to be in generic position, and now I want to relax this condition. In fact, I specifically would want the monodromy not to be in generic position, but rather to be of the following Jordan type. So you can diagonalize it, but then you have a bunch of eigenvalues coinciding, all but one, all lambdas, and then, well, the last one has to be lambda to the power 1 minus n. This is the same as asking that the monodromy matrix minus certain scalar matrix is of rank 1. So our S here stays for Ruijsenaars-Schneider. It's this moduli space is the phase space of a classical integrable system, classical Ruijsenaars-Schneider integrable system, classical Ruijsenaars integrable system. And of course, if n is equal to 2, then this condition is void, as long as we ask that monodromies are generic. And, well, kind of fact that, well, kind of, I honestly didn't know who to attribute it to, because indeed, somehow, classically, the statement is almost obvious, right? That the spherical Daha, if you take Q equals 1, is actually algebra functions on that moduli space of local systems. So how so? Well, if you take a punctured torus and you have two cycles, well, green and orange here, right? These cycles generate pi1, and you can take monodromies around the cycles, you can take their traces, and, well, so when I say traces, I mean trace in kth fundamental representation. Right? So sum of all principal k by k minors. And, well, trace along, say, green cycles will be ek0 in kth fundamental representation, and trace along the orange cycle will be e0k. Right? You still have an action of gamma s, which is SL2Z, so that's how I would like to think about the spherical Daha and SL2Z action. So now, as we have some geometric intuition of what's going on, we can now try to construct this representation that we were talking about. I will not I will not give it definitions, but I'd rather like to show the tools that I'm going to use for that and some properties of these tools. You know, just sort of as an advertisement of the subject rather than, you know, proper introduction to it. So the upshot of what I'm going to say is that this variety that we're considering has cluster structure. So it's a cluster variety in the sense that Misha was explaining. And as a cluster variety, when you have quantized that, any quantized cluster variety or quantized algebra functions on the cluster variety comes with a certain mapping class group equivariant Hilbert space representation. So the type of representation we're precisely looking for. And PGS, sorry, G here means group, S here means punctured torus, and group is SLN. RS means Ruijsenaars-Schneider. So this variety that we were looking at, that we're interested in, our phase space of our Ruijsenaars system, is an example of cluster variety, right? So it has this representation. So that's what we're going to use. Now, what is this quantum cluster variety? Well, as any variety, it is covered by charts. Except for, well, usually when you have a variety, you cover it by C to the n charts. And in this story, I would like to cover it by C star to the n charts. Now, usually if you have a variety and you think this variety has to be phase space of some integrable system, well, you say, okay, if we can find local Darboux coordinates, fantastic. If we can find global Darboux coordinates, well, chances are it will not happen. But if we manage to find global Darboux coordinates, it just means that we're in a very, very boring situation. That's not the case for clusters. So morally, what's happening here is you replace C with C star, and then instead of Darboux coordinates, you look at exponentiated Darboux coordinates. So instead of x and d over dx, you're looking at e to the x and e to the d over dx, or e to the I d over dx, or I is imaginary union. And that actually allows you to get sort of global exponentiated Darboux coordinates without your variety being extremely boring. You have a lot of interesting examples. And if I haven't convinced you so far, then sort of everything that lives in this trigonometric world, think of trigonometric R matrices, or maybe there are zero modes, quantum groups, so on. They're all kind of RTT algebras, with R being universal R matrix for a quantum group or quantum affine algebra. All of those have cluster structure, and classically they are cluster variety. So more formally, you have an atlas of quantum cluster charts. What's written here is just a quantization of a C star to power k in this case. And so before I said we will have exponentiated Darboux coordinates, but when we quantize, they just become Q commuting operators. Right? Now, these charts are like, and if they're Q commuting operators, you have to label these powers of Q by something. So you can as well write, you can introduce some elements epsilon rs. This is just numbers, and the computation relation is Q to the epsilon rs yr ys equals Q to the epsilon sr ys yr, where epsilon rs is equal to minus epsilon sr. So epsilon is a skew-symmetric matrix. And you can think of this matrix as matrix of a quiver. So this quiver, it has k nodes, one node for each generator, and epsilon rs is just sign adjacency matrix. So this is number of errors from R to S minus number of errors from S to R. Or you can put it upside down, start with a quiver, get this thing that we just call the quantum torus, right? This is your chart. If you have charts, then you also have to provide some gluing data. Well, and what is gluing data classically? Classically, it is, well, you have one chart, you have another, you have an overlap, and on the overlap, you have to tell how you rewrite one coordinates in terms of others. So, which means on the algebraic level that you have global algebra functions, you have localizations for each chart, and on the overlap, you have an isomorphism between even further localizations. But what you can always do, you can just take a chart and take its field of fractions. We'll have to be slightly careful here, because this is a non-commutative algebra. You cannot take its field of fractions. So when I write this, I mean skew field of fractions or non-commutative field of fractions. And for some algebras, you can do it. And if your algebra was a quantum torus, you can definitely do that. Right? So this is field of fractions for the algebra which was a quantum torus. And a cluster mutation is just this gluing data, just an isomorphism between fields of fractions of the corresponding functions of algebras functions on the chart. Now, what implicitly said here is you start with a quiver, and then you can mutate this quiver once in each direction, and then you can, take another quiver and mutate it again. So you have a k-regular tree of charts, and you have some notion of adjacent charts. That's maybe a new thing. Well, new sort of compared to the old story about varieties. And then you have global algebra functions, which is called universal Laurent algebra. And why is it called this way? Well, just because classically, if your charts are C star to some power, what's algebra of functions on C star to some power. There are Laurent polynomials. You see, if it was just C to the n, there were just polynomials, were regular functions. If it's C star, it's Laurent polynomials. And universal Laurent things is those, you take any chart, take Laurent polynomial, start mutating it. So start rewriting these in coordinates of adjacent charts and again and again and again. And you just need to make sure that you stay Laurent polynomial over any finite sequence of mutations. If it's true, then this is a global function, and that's an element of universal Laurent algebra by definition of that thing. Right, so this is quantized algebra of global functions on our cluster braid. Now this is an example. So this is a punctured torus, and group is SL2. I did not explain, and I will not explain how to, given a surface and the group, how to produce a quiver, but it's known. If you give me a group and a surface, I can produce you a quiver of that cluster algebra. Here's one for G punctured torus, for GSL2 surface being a punctured torus. Now, since it's a torus, you have to glue vertical sides and horizontal sides together. It's called amalgamate, and that's the quiver, the Markov quiver that you get from here. And this is an example of of a chart corresponding to this quiver, right? For if I is in Z mod 3Z, then Q square I yi plus 1 equals Q to minus 2yi plus 1 yi. Now you have a mutation, and again, just to give you a flavor of what kind of special functions appear in the story. So mutation, you can think of this mutation as two-step process. So step number one, you do some monomial transformation. So y primes are new coordinates and y's are old coordinates. And so first you take your old coordinates, y3, y2, and y1, and you do monomial transformation. So y3, that's the place at which you mutated, becomes y3 inverse. y2 just stays as it was. And y1 becomes a product of y1 and y3 squared with some power of q. And all of this can be read from the arrows in the quiver. So that's some very hands-on monomial transformation. What you do next, you conjugate by a cube of Gamma symbol of y3. Now this is this guy here. It's product for j from 1 to infinity, 1 plus q to the 2j minus 1x, all of it inverse. It's known as q logarithm or q exponent or q gamma function. Pick your favorite name and your favorite function and use it. So that's an example of how this algebras look like. Now, with all that in mind, let me explain why having that algebra, you have an action of the mapping class group. Well, so imagine that you started from a quiver, and then you mutated, and then after maybe 50 mutations, you arrived at a quiver which is isomorphic to the one you started from. So I did not tell how the quiver mutations look like, but I'm sure Misha did, and this is some very easy combinatorial rule. For example, in this case, any mutation will give you an isomorphic quiver. Isomorphic meaning the same up to permutation of variables. So suppose you arrived at quiver Q prime, and Q prime are, I wrote equal, I should have written isomorphic. And if they're isomorphic, it means that there is a permutation of variables or permutation of nodes such that the quantum torus from quiver Q just isomorphic to quantum torus from quiver Q prime, and the isomorphism is given, yj goes to y sigma of j prime, where sigma is some permutation, just by definition of this quantum tori and definition of isomorphic quivers. And if you have that, then this is kind of cool, right? Because what you can do is the following. So you start from a triangulation of your surface, and then an element of the mapping class group. And first, you take gamma inverse of a triangulation. If you take triangulation and apply Dane twist, you get an isomorphic triangulation. Isomorphic in terms of how triangles are attached to each other. So this gamma inverse of triangulation is just isomorphic to triangulation. And therefore, quivers are also isomorphic. Again, I did not explain how to hook up a quiver from triangulation, but you'll probably believe me that if I'm half reasonable, given isomorphic triangulation, it should give you isomorphic quivers. And then you can do this. You can start with chart with original triangulation, mutate it, many times until you reach triangulation of gamma inverse of that and apply a permutation, right? So this is done by sequence of flips which change triangulation. It corresponds to a sequence of cluster mutations, and then you apply permutation. And this defines your action of the mapping class group, right? Because now it's an automorphism of a chart, but the only thing you did quantum mutations, you did cluster mutations and permutation of variables. So if something was Laurent when you started, so if you took an element of universal Laurent algebra, you mutated it, it stayed universal Laurent because it was a global function, and then you apply permutation of variables, it's still universal Laurent, right? So you get an automorphism of universally Laurent algebra, automorphism of global algebra functions. The only thing you need to be worried about is that, well, when I say that you can go from any triangulation to any triangulation by just sequence of flips, well, first of all, you have to make sure that yes, indeed you can, and well, that's a well-known statement. But then you have to make sure that, say I started from triangulation over here, and I end with triangulation over here. I can do two different sequence of flips. How do I know that the transformation that I produce does not depend on the sequence of flips? And the way I know it's well. Here it's it's called the pentagon relation. So if I just do flips of diagonals, I get the same thing. But that means that this function that I conjugate by should also satisfy some version of pentagon relation. And again, it's by definition of quantum dilogarithm, it does satisfy pentagon relation. So in other words, well, I didn't write it down, but psi q of x times psi q of y would be equal to product of three dialogues with slightly different parameters. Okay, so hopefully by now I convinced you that if you have a quantum cluster variety, well, again, if you haven't worked with it, maybe it looks a bit slightly clumsy and big construction, but at least what you do for sure you have an action of mapping class group on that algebra. In terms of representations, right, so let me again, just one word about representation of these varieties. Well, again, same example, and if you want to construct a representation, well, remember, we can think of these y1, y2, and y3 as sort of, at least when I wrote uppercase y1, y2, y3, the Q-commute, I can think of those as exponentiated Darboux coordinates. And lowercase y's, I want to think of those as logs, so as actually Darboux coordinates. And now what I'm gonna do, I'm gonna choose what people call polarization, which means that I'm just gonna assign some elements from actually a Heisenberg algebra so that the commutation relations are correct. And this is just one choice. There are plenty of choices, infinitely many, but just one choice of how you can assign position and momentum operators, and tau here is just a Casimir, so that commutation relations work, right? So x is position, p is momentum, which means it's 1 over 2 pi I d over dx. Tau is central. And then if you take a commutator of yj and yk, it's 1 over 2 pi I epsilon jk, where epsilon jk is the sign adjacency matrix. As soon as this is correct, then you can send your quantum torus to an algebra over rational functions of q and t, generated by e to the p and e to the x, by sending uppercase yj to e to the 2 pi b lowercase yj. So here, b is real, q is e to the pi I b square, t is exponent of tau, well, with some constants. So all this 2 pi b and pi I b squared, this is just just to make formulas work, it's just some normalization. The reason for having b real is if you wanted your action of mapping class group to be unitary, you need to ask for b being real. If you don't have to ask for b being real. Now, why on earth would you want the action of mapping class group to be unitary? Well, because the moment so how do you cook up representations? Well, in the usual world, you have an algebra, you have a bunch of localizations, but usually algebra is given by generators and relations. You take generators and relations, you construct a representation, and then you can localize it. You can construct representations of localizations. Here it's sort of upside down. You don't have generators and relations description of this algebra, but you very much do so of any localization, any chart. So instead you construct a representation, pick your favorite chart, construct a representation of this chart, and pull it back to your algebra. But then you have to make sure that somehow, well, you construct a representation from one chart, from another chart, and you have to make sure that when you pull back, these representations are equivalent, are isomorphic as representations of your algebra. But even before that, when you try to act by these operators on something, well, what you can act on? Well, of course, you can act on some polynomials of e to the x. That's one choice. But that's not what we want, because we wanted delta functions to be in there. So what you do instead, you try to act on L2 functions of x. But you can't really, because e to the x and d to the I d over dx, they're unbounded operators. So you can't just act on L2 functions. And instead, you have to be careful. You have to use some functional analysis. You have to carefully define the Schwartz subspace on which they act. And again, if I'm being completely honest, you have to take Schwartz subspace and like dual to the Schwartz subspace in a sense, so that you have delta functions. But that's, again, this is maybe a slightly non-canonical part if you like discrete integrable systems, but it's something known in representation theory of groups like SLNR or their quantum versions. That's a standard procedure. And what you need to do, so this is some Schwartz subspace, and what you need to do, and what Falk and Gonschow have proven, is that if you take two different charts and you construct these two different Schwartz subspaces, then they're unitary equivalent as modules of that algebra. And on top of that, this whole construction is equivariant with respect to the mapping class group, right? Because let's just think of it. So mapping class group acted on your algebra by just conjugating. So you had an algebra, you had some element of an algebra. Mapping class group acted by conjugating this element by something, right? So then you just need to take this something and act on your representation. And then it's just like linear algebra 101, when you have an operator, you have a vector, you take change of basis matrix, you conjugate your operator with this, and you act on a vector with that, right? So that's just change of basis, that's it. And that's how mapping class group acts on representation. And again, examples just so if you like Toda systems, maybe you will recognize that as Toda Hamiltonian. Again, example of how that works in this particular quiver. So the only thing I'm doing here, I am computing, and I'm not going to spell it out carefully, but I'm going to refer to Misha's lectures. And if you haven't attended those, maybe you'll just trust me. So I'm taking the surface and I'm computing trace of the monodromy, right, around this horizontal cycle, and trace of the monodromy around vertical cycle. When I compute trace of the monodromy around horizontal cycle, I get expression in terms of this e to the lowercase y's, right? And this is expression in terms of y's describing this horizontal monodromy. So it only depends on y1 and y2 as it should. And if I take vertical monodromy, it only depends on y2 and y3, but it's very same expression. And if I wanted, if I wanted -1 cycle, it would be similar expression, but in terms of y1 and y3. And when I plug in this polarization in terms of x's and p's and tau inside y1 and y2 and y3, this is what I get. And this is literally quantum, it's Hamiltonian of an open quantum Toda chain for SL2. And this is some other operator that depends on t, which is, remember, it's exponent of tau. Which you probably don't recognize, and you have no reason to recognize that. Some expression that you get. Now, remember, we have action of the mapping class group, so indeed, we still have a Dane twist. I'm not going to write formula for it, but this Dane twist is, again, so if you like, by any chance, if you like Toda systems and you like discrete integrable systems, then there is some such thing as a Q system, which is a discrete flow commuting with Toda Hamiltonians. And in this description, this is nothing but just the Dane twist along that cycle that we use to define Toda Hamiltonians. Yeah, so it's one-step evolution of Q system. But of course, you could have chosen this, this cycle 1, 0, but you could have chosen any cycle. Take any two integers k and m, take Dane twist along that, and that will give you a discrete flow.
How the Dane twist is described by mutation in this case?
Yes, I can. Right, so here the Dane twist is actually very, very simple. You mutate at So it depends on whether you want the twist or its inverse. But you mutate at y1 and do some. So you mutate at y1, you obtain a quiver where with all errors reversed, and then you just have to do the symmetry along the vertical line.
Yes.
And that just tells you some Gaussian by which you have to conjugate.
Yeah.
Right. So it can. So your Dane twist will consist of two things. First, you apply quantum logarithm, and then you apply some Gaussian, and that's it.
So a single mutation, basically.
For SL2, it's single mutation. For SLN, it's n mutations. For SLN, it's n-1 mutations. But
with this quiver?
Well, this one is for SL2.
Oh, yes.
So for SL2, it's one mutation.
I see. So in SLN case, you prepare a more complicated quiver for this punctured torus.
So if your group is SL2, then all the quivers will be just isomorphic to that. Because Markov quiver, you can mutate as many times as you want, it will still stay Markov quiver. With SLN, of course, you can have a very complicated quivers, and then number of mutations will just depend on the chart you're in.
Yes, but my question is, in SLN case, you also use this punctured torus.
Yes.
Good,
yes.
Thank you.
All right. So with all this being said, now the only thing that remains to be done is somehow take our spherical Daha and embed it into our quantum cluster variety. And again, the idea is rather trivial. So you have spherical Daha, and it's generated by EK0 and E0K. Right? And you have a faithful representation where EK0 went to elementary semantic functions, and D0K went to McDonald operators, right? So that's what we saw on the first slide. Now, if you have SLN local systems on a punctured torus, you still have traces along cycle, like with horizontal cycle and traces along vertical cycle. So you have LK0 and L0K. And again, you have a faithful representation. Well, LK0 becomes higher Toda Hamiltonians for, kth Toda Hamiltonian for SLN. And the L0K becomes these operators that I call L0K hat, which is the analog of those unrecognizable things. Some Laurent polynomials in e to the x and e to the p. And remember, EK lambda, they're eigenvalues of Toda Hamiltonians, right? Oh, sorry, maybe not remember. I haven't said that, but I'm telling you now. So if you wanted to, so what should be the relation between these guys and these guys? If you look at eigenvalues of Toda Hamiltonians, they're elementary semantic functions. And that should somehow tell you that the connection between this side and that side should be, you should take a spectral transform of Toda system. And then Toda Hamiltonians will start acting by elementary semantic functions. So let me now make it more formal. Indeed, you can find what people call Whittaker functions or Q-Whittaker functions for Toda Hamiltonians. And these are just eigenfunctions for your Hamiltonians. And the eigenvalues are elementary semantic function of e to the lambda 1 up to e to the lambda n. Or again, with the condition that lambda 1 times dot dot times lambda n is equal to. There were theorems by Rinat for SL2, by Gus and myself for a high rank, that this whole theorem basically says that Toda Hamiltonians are, eigenfunctions of Toda Hamiltonian, this Whittaker function, they're orthogonal and complete. So you have a basis of your Hilbert space, or whatever space you act on, just given by this Whittaker functions. More formally, you have a unitary equivalence between L2 functions of variable x and kind of symmetric L2 functions of variable lambda with some measure, where what's written here is just, it's really like a Fourier transform, except for you use, instead of plane waves, you use Whittaker functions. Right? And this gives you unitary equivalence. Now, on this slide, I said that, okay, all is good if we take punctured torus and we take SLN local systems and we take two traces. But then, remember, this was a bit too big of a space. So what we really needed to impose some conditions on the monodromy that is not generic, but rather all but one eigenvalues coincide. And I claim that you can still do that. You'll still have these elements, LK0 and L0K. And if you do that, if you impose conditions on the monodromy, take quiver corresponding to that situation, this quiver in bracket just means that it's kind of, this algebra doesn't depend on a particular chart, depends on the mutation class. So this is the mutation class of the quiver. So this thing here is what quantizes our phase space that we're interested in, this phase space of SLN local systems on the puncture torus with a condition on the monodromy. And if you've done that, then L0K, after you've applied it to a Whittaker function, just becomes Macdonald operator applied to the Whittaker function. If T is equal to 0, then what you recover is the standard story about bispectrality of the Toda transform. Right? Because on one hand, Toda Whittaker functions are eigenfunctions for Toda Hamiltonians, but on the other, they're eigenfunctions for T equals 0 Macdonalds. Now here, of course, we see that they're not. What it means is if I set T equals 0, then over here these operators will lose dependence on the momentum operator, so they will become multiplication operators. But if T is not equal to 0, then of course there's some Q difference operator on this side as well, right? So lambda here is multiplication by e to the lambda, and D is shift. And so just the theorem that we get is, again, for n equal to some folklore, for n greater than 0, it's not yet written, but it's a joint work with Rinat, Philippe, and Gus. And we actually have an SL2Z equivariant embedding of spherical Daha into that quantum cluster algebra that we discussed, where EK0 goes to LK0 and D0K goes to L0K. And the idea of proof is what we just discussed, right? So how do you construct this embedding? Well, to construct an embedding from one algebra to another, you better have some control over generators and relations, and you don't here. But what you do, you have a faithful representation of this algebra, and you have faithful representation of that algebra, right? And you have a unit equivalence between the two spaces that they act on, right? So you can take generators of this algebra, look at what operators they become, when acting on this space, and then just recognize those as images of some generators of some elements from this algebra. And that's how you get an embedding. And you can check indeed that it's SL2Z equivariant. Now, in the last 2.5 minutes, how do you finally construct eigenfunctions? Well, now you can actually perform the strategy that we saw on the first slide, on the second slide. So you start with elementary symmetric function, lambda plus lambda inverse, and Macdonald operator, right? Just SL2 case for now. You act on the space of this symmetrical to functions of lambdas. Then you do Whittaker transform. You start acting on L2 functions of X, and your elementary symmetric function becomes Toda Hamiltonian, right? Then here you can apply an S transformation, and your well, I don't know where Toda Hamiltonian goes, but this L01, which Macdonald operator was mapped to, becomes now Toda Hamiltonian, because L01 became L10. And after you apply Whittaker transform again, this H1 now is diagonalized, and it becomes multiplication operator. Right? So if you go kind of across these three sides of, well, whichever way you want to go, three sides of this diagram, you turn your Macdonald operators to multiplication operator. And therefore, your eigenfunction of Macdonald, how do you construct an eigenfunction of Macdonald operator? Well, you start with an eigenfunction of multiplication operator, so delta function, delta of mu minus t. You apply inverse Whittaker transform, which is again just integrating against Whittaker function. You apply S transformation, you apply Whittaker transform, right? Now, if in this operator you take integral over t, it just becomes an S transformation sandwiched between two Whittaker functions. So this is nothing but a matrix coefficient of an S transformation, right, evaluated on two Whittaker functions. And this is your Macdonald eigenfunction. So in other words, if you take Macdonald operator, apply to this function defined by this matrix coefficient, you get e to the mu plus e to the minus mu times that function. This is actually quite useful because, well, maybe I haven't said that. I can say that informally that this space was kind of symmetric in lambdas. The Whittaker function is symmetric in lambda in this lowercase in the subscript. So it's symmetric in lambda and mu just by definition, more or less. So that's why you for free get, of course, all these properties that you have symmetry in mu, you have symmetry in lambda. It's rather easy to show sort of if you swap lambda and mu and t tau to minus tau, or t to t inverse, it would be in exponentiate. You still have this symmetry. And yeah, this formula actually recovers some known formulas that from Ruijsenaars paper for SL2. I have to finish. I'll take, if it's okay, I'll take 20 seconds more. And formulas for this recent papers by Belousov, Dergachev, Kharchov, and Haroshkin for high rank. Also, even if you came up with this formula, just somehow you guess this formula, maybe you calculate this formula. If you want to show that this indeed, so if you, after you've shown that it's an eigenfunction for Macdonald operator, you then need to show that these eigenfunctions are orthogonal complete. In what we did in this approach, you absolutely don't have to do this, right? You just get it for free because you started with something complete and then you just applied unit transformations. So that comes for free. And Macdonald polynomials, if you're not interested in all this Hilbert space nonsense, if you just want polynomials, it's totally fine. You just take this function and you evaluate it at special integral values of your parameters, which is done by just residue count. This is, in principle, this is of course some contour integral. You evaluate at special integral lattice, you do residue count, and you recover Macdonald polynomials this way. So conclusion, if you have SL2Z equivariant Hilbert space representation of spherical Daha, then you can get Ruijsenaars wave functions easily. You can get Macdonald polynomials easily. What you will need for that, you will need quantum cluster varieties, because they literally provide you this tool. And this, of course, it's not just a story about spherical Daha or about Ruijsenaars system, but any system that comes from whose phase space is some moduli space of local systems on a certain surface, and most systems I know at least are such, you can use this strategy. And of course, let me just add with a slogan that would be really cool if you can approach some questions in Macdonald theory, which is just questions about polynomials, via this Toda chain and clusters, and that's something that's kind of currently under discussion, and we have some hopes. Thank you.
Okay, so maybe I didn't understand. So for me, it was quite difficult. But so I've seen multiple times the Sklianin measure.
Yes.
But I've never seen the QT Sklianin measure. Is it because it never appeared, or is it because it was trivial?
Sklianin measure does not depend on T at all, but Sklianin measure is a product of these quantum Dal logarithms. So Q is intrinsically in there. I mean, to be precise again, so we discussed Q-Gamma symbols, but what
So
should have done is Faddeev's dialogues.
So Macdonald polynomials are orthogonal with respect to what Macdonald calls torus scalar product.
That's
and
right.
that's what I would call the factor that appears in the torus scalar is the QT Sklianin measure, I would say. So you only have the Q Sklianin measure.
That's right. That's actually a very good observation. So Sklianin measure is something that appears in this Whittaker transform. In this Whittaker transform, this Whittaker transform does not depend on T at all.
Not 0 T, forget T.
But what does depend on T is the S transformation. Okay. So in this formula over here, the only part that depends on T is not the two Whittaker functions, but the S, right? So somehow Sklianin measure is what attached to the Whittaker functions to size. And there's all the dependence on T is hidden inside here. So you can absolutely recover this orthogonality and completeness orthogonality of Macdonald polynomials from here, from orthogonality and completeness of these functions. But the measure that you'll have will not be Sklianin measure, but it will rather, you can compute it easily. It will depend on T, but it will be different from Sklianin measure. Because Sklianin measure is something that is responsible for, I forget, either orthogonality or completeness of Whittaker functions, not Macdonald.
So let me ask a further question, if there are no questions. So can you, suppose you don't know the book of Macdonald. Suppose you don't know the book of Macdonald and you want to prove that the Q-Whittaker polynomials are orthogonal with respect to this Q Sklianin measure. Can you do it with your talk?
Yes, absolutely, yeah. So in fact, here I did not know, yeah, very good. So let me try to reinterpret your question. So when you say that, suppose I don't know anything about Macdonald's, I want to prove something about Q-Whittakers, right? So I think you're at this point, you're probably thinking that, look, let's think of Q-Whittakers as t goes to 0, as McDonald's at t equals 0, right? Good, right. So, yes. When I claimed over here that I can recover McDonald polynomials as special values of McDonald function, which I discovered by, I knew nothing about McDonald functions here at all. I discovered this guy, right? I can do absolutely the same thing with Whittaker function. I can take Whittaker function, specialize it at certain integral lattice, and recover Q-Whittaker polynomials. And indeed, orthogonality completeness of Whittaker functions will provide me with the orthogonality of Q-Whittaker polynomials, very, very much so. Moreover, maybe since we're discussing this anyway, not really this talk, but something extremely close that's also written is that you can get a decomposition of McDonald polynomials into Q-Whittaker polynomials from this setup, more or less for.
And the coefficients are explicit or easy, or they are just?
Coefficients are very explicit and easy. They're, again, you do some residue count, which becomes just a summing over integer points of some, well, in SL2 case, of some segment, but in SL1 case of some polyhedron. The problem is this coefficients, unfortunately, these coefficients are not positive. But then it's an explicit. They're explicit, and then you have explicit description of t equals 0 McDonald's into Schur's, so you can hope to actually get something explicit. Maybe look at cancellations and at least have some statement very explicit for symmetric McDonald polynomials. That's one of the hopes, but that hasn't been done.
Okay, I think we're out of time, so we'll save questions for lunch. Thank you very much.